Welcome everybody to Lecture 5, Databases and Information Systems in the winter semester 25-26. A little bit late due to technical problems, but we will catch up. I will catch up by talking faster. I will say something about your experiences with exercise sheet 4, which was about coding a simple RDBMS in Python, which was a pretty cool exercise, which some of you did, some did not. I will talk about this. Then we have some new operations today: join, grouping, order by, and more SQL. And the exercise sheet 5 will be to continue exercise sheet 4. Even if you did not do exercise sheet 4, you can just resume from the master solution. So even if you did not do it, please do this exercise. It's absolutely worth it. Here are some of your experiences. I really liked the lecture, and the sheet was surprisingly easy. We will also see in a minute the opposite opinion. Very good exercise and very good frame to work with. The code templates are, as always, top-notch. Thank you. So Robin is responsible for this, who is sitting over there. Implementing the operations was easy, but queries took ages. We only have Cartesian products so far. Took me 7 hours and taught me that Cartesian products are bad. Yes, indeed. My story with this exercise sheet is one of great frustration, dumbness, and amazement at the end. Exercise 2, very tough. I think this is not too bad when it's, frustration is always a part of learning, sometimes more, sometimes less, and if it ends in amazement, I'm happy. Exercise 2 was very hard. The sheet took me about 9 hours. So there was a spectrum of people, as we can see. For some it was easy. For some it was harder or hard. This was an extreme opinion, but I did want to include it. This exercise was extremely frustrating. Took me nearly 20 hours and I couldn't even finish everything. That was an outlier, but I did want to mention it. Question of the week: what annoys you most about HIS-in-1? The load times when clicking through the Studienplaner feels like it definitely calculates Cartesian products at every step. And I swear, if you look in the code, you will find quadratic algorithms all over the place and Cartesian products and stuff. It's the truth. It's not even a joke, and it's people who didn't pay attention in class. So please don't become one of these people when you work in a real job later in your life. Pay attention now into the exercise sheets, and you will do humanity a great favor. Definitely that it is HIS-in-1 on this slide, so slow. On the other hand, this gives us HIS-in-1 hate, which is quite entertaining. We just got more of that. The insane time it takes to look certain pages. And it's true, it's insane. I mean, the data in HIS-in-1 it's a few students, few 10,000 students lecture. If you do research with us, we have like 1,000 times more data and it's faster. So it's not large data, but for it's just terribly bad design and implementation. Every time I want to do a math lecture, I have to call 3 people so that they can add the course as an option. So that's not about performance, but about features and also how people handle it, I guess. Everything that comes with an oldish PHP website. Actually, I didn't know that HIS-in-1 is PHP, but this by itself says something. I think PHP is something for the museum, not for serious website. In September 2020, that's not true. I think it should be 24 here. I mistyped. They took down the grade overview, Notenspiegel. Then there were some problems. They took it down, never fixed it. Yeah, this happens very frequently. So a lot of annoyances. It does not remember my login on my PC, only on my phone, so a lot of usability issues. Okay, that was a fast going through the last sheet and so on. If there are no questions or more HIS-in-1 comments, I will just continue with the lecture. So we have a full program, but it's not too hard. But again, please pay attention, and there's a lot of stuff we do together and try to think while we're doing it, so that you benefit from being here in class. Same for the people on Zoom. You can just write in the chat whenever I ask him. So ask something. Join operation. So here's a pattern we have seen a lot. This is a query from the last lecture. We have seen it in many variations. You join something, so here you have 3 tables which you join, which is how we implement it so far, 2 Cartesian products, which are crazy expensive and you should never do, except it is still done in some systems, we know. And then we have where and 2 equalities. And this is an extremely frequent pattern. So let's just pick one join from this, 2 tables, and then you have an equality constraint which joins the 2 tables. And this, because this is so frequent, we have an operation specifically for this combination, and that operation is called a join. There are many types of join, and the most important and most frequently joined is the single column equi-join. I will explain single column equi and join in the following. That's the signature. Might look scary. I mean, I always include the formal definitions. It's not necessarily to, maybe you can understand them right now in class. Otherwise, understand them afterwards. It's not really hard to understand. Maybe it just takes a little time. The comma here, let me just quickly correct that. If these live edits are annoying, please tell me, and then I will not do them during the lecture, but afterwards. So you're joining 2 tables, and you have to say on what you join, where you have the where equality thing, and that is the 2 columns. So you have a column J1 in one table, J2 in another table, and you have this beautiful bow tie, so what men sometimes wear for festive events, it's called a bow tie. Yeah, it's this thing which you wear here. T1 join T2, and you just as a subscript write the join columns. So the columns is just the columns, they are domains, and the rows are the 2 tables. And then the column indices can be more than 1 column, but we often do 1. And this also looks more complicated than it is. The result is the Cartesian product almost, but only those where the rows, the combination of row from the one and from the other table satisfy this constraint. And this is not right? It should not be an X here. It should be a different column here. Okay, but let's see an example. And here we have 2 tables. I will use this example or a variation of this a lot in the following. So we have 2 tables, professors and the courses they teach. So here we have 4 professors, one of them gone already from us, Thomas Brox, Frank Hutter, myself, and Wolfram Burgard. Here IDs of courses they teach. And here we have courses and the students in them. So just some number, maybe Matrikelnummer, whatever. And you already see some interesting things here. So here 2 courses which are taught by, have 2 lecturers, and this same course, which is 2040, has 3 students. So, and now we do a join. So we join on course, so on this second column. And this is the operation. So this is now a Cartesian product followed by a where clause with an equality thing, and this can be written as one join operation. So first ask if anything is not perfectly clear about this. And you can, again, in SQL, in basic SQL, it basically reads like language. So we are joining these 2 tables on this column, a course column. And as always, the output is another table. And this is the other table, and let's take some time to understand this. And to understand this, let's look at one possible value in this course column, let's look at all the rows where, just for example, what I just show is just to show one example. So let's look at these 2 rows, which have V0242 as a course, and the matching rows in this table, and we just put a frame around them here, are this one. Yeah, sure. This is just wrong. And this one, let's just keep it open for a moment. So this is everything with 2040 in this table and in this table. What's happening? Somebody just noise, just making noise for fun. I think we just bear with it for a second. So what happens if you, and as you can see, we have a part in this table which is just the result of this join. And you see something interesting here. So it's not a full Cartesian product of these tables. Please tell me, if we compute the full Cartesian product of these two tables, how many rows would it have? How many rows would the full Cartesian product of these two tables have? This one and this one. 24. Yeah, it's 4 and it's 6, 4 times 6. This does not have 24, right? It just has 1, 2, 3, 4, 5, 6, 7. So the join produces something smaller. But let's just look at part of the result. Namely, it's these two rows, which is one lecture taught by 2 lecturers with 3 students. It's a small class in my example. And now here we have a Cartesian product on a smaller scale. That's important to understand. So even with the join, you still have Cartesian product effects if you have something like this. So now just the part of the join, which is the result for this, is 2 times and actually I did a mistake here, right? This should extend one more. It should be 6. And let me just, so actually most of the result just comes from this one lecture. Yeah, so it's just all combination of these 2 with these 3. That's what the join is. Because in every combination of these rows, the course here is the same as the course here, right? If I have 2 here with that course number and 3 here, I have 6 rows in the result. And as usual, I just put the whole row from here, which is this part, and the whole row from here, and so on. And let's maybe, also there's one more in the result. Let me go a little bit slower in the beginning and then faster. So we have this course here by myself, and it's a very small course with just 1 student here. Yeah. And this is, now it's just one combination, and this is this row. And all the others are not included in the result because, 720, I don't have it here. 2060, I don't have here. 1303, I don't have here. Any questions about this? This is just the semantics of join. Okay, let's go on. So why single column equijoin? I think it's easy to understand. It's called single column because I'm joining on one column, right? This is course. So it's this one column where I'm looking for equality. So I'm looking, is this equal to this? And this explain, equi. So it's an equality constraint on one column. You could have more columns. You could have other constraints. I could say, is this value here smaller than this value here, and so on. If the condition could be true every time, or whatever the condition is, then you can have the full Cartesian product, right? This could happen for a join, but typically you get a subset. So let's just go back to query planning. So this is just the same query again, which we have seen. So this is the sequence we would have had in the last lecture because we didn't have a join operation. We would first compute the Cartesian products of the 2 tables. Now we have all combinations. Now we just pick the combinations where, let me just put we did it, we just did it like this. In the Cartesian product, this is column 1, 2, 3, 4, and if we want to say this should be equal to this, it's R2 equal R4, and now we can just do this. So if we have this operation somehow implemented, we will talk about implementation in a second, then we could have this sequence of operation. And now we will talk about how to implement this. Any question about this so far? You just ask, or please use the chat, and I will just continue. So, hash join. There are 2 kinds of joins, hash join and merge join. We will start with the hash join. And for the exercise sheet, let me jump back and forth. This is the exercise sheet for exercise 5. So the first exercise, part 1, will be to implement a join operation, namely a hash join, which is why the hash join, it's relatively easy to implement, as you will see. And it's simple. It's also reasonably efficient if you do not know anything about the table. And it will become clear what I mean by that and how you could benefit from knowing something about the table. A little bit of notation. So the rows of the first table, it has n rows. We just call them x1, xn. We call the table x for now for notation. And now this table, you might have some duplicates here. You just look at the join column and you take the set of distinct values in the join column. This will become clear in a second, but it's good to try to understand simple abstract things. If you don't understand it, you will understand the example in a second. We will compute a hash map, which just remembers for each possible join value which join columns there are, and then we do this. I think the rest, I just leave it there. We will just do it by an example now. Let me just, maybe go back and forth, maybe not. So let's just do which color do I pick? That's a good question. Maybe I pick blue here, but the right blue is important, this one. So my hash set, so my, so first, so this is my table. This is my table Y, and this is my table X. Danke, Frank. And so my set K, and this is just from the previous slide. This is the join column here. Join column of X. What's the set of distinct values in the join column? So I want the set of distinct values. That's 720. That's one of the values. It's V2040 and it's V1304. Yeah, that it's there twice. I just want to know set of distinct values. There are just 3 different ones. And let's now look at the hash map. And the hash map is called H. So what the hash map does is, the hash map, and let me just write it like this, hash map H, and it maps V0 to 0 to, and what it does is for each, this is the row indices, let me just call them 1, 2, 3, 4, and here I just call them 1, 2, 3, 4, 5, 6. And now I just remember for each, so this occurs in row 1, V2040, and this here I have, it's a set, the order does not matter. What's the set here? It's the set of row indices which contain their scores. What's the number? What's the right set here? 2, 4, yes. 2, 4. And then I have, so it's 1304, and that's 3. And now, let's go back to so now I have this hash map, and this is the hash map I just computed. Now I go over the rows in the second table in any order. There's no ordering with the join operation. I just go in some order now. And now for each row, I just check, is the value in the join column contained in this hash map? And if yet, then add the corresponding rows to the results. And let's just do that now. So for each, and now iterate over, let me write it like this, iterate over Y. And let's not just do row 1. So I check row 1, 13, it says 1304. And so now I have, what do I have? I have one match, right? Let me just write it like this. Matches, let me write it more specifically. Matches rows. Matches row, how do I, matches X. So I called the rows X. Let me do the following, because on the previous slide I gave these X1, X2 and so on, so that it matches the notation. And you can do it yourself in your head and check whether everything I do here. That's the notation I used on the previous slide. And if everything is clear to you already, you can start doing first part of the exercise sheet. So this matches X. It matches X3, right? This here matches X3. So here, in this row, V1304, I look it up in my hash map. My hash map says it's there, and it matches row 3. That's how the hash join works. So I have a match in row 3, and so what will I do? I will just write into my result, and let's do that here, the row 3, which is my name, V1304, and this row, which is 7383436. And now this is a thing for now. We just, the join column, it's an join, so the join column will just be the same. Of course, in practice, you will not have it twice, but for simplicity, we just have it twice now. So now let's take the second row. So now, and maybe let me not write 1 here, but let me write Y1 here. So, and that's now the second row is Y2. What's the value in my join column? And the value is 2404. And now this matches. And now I look it up in my hash map. And in my hash map it says, oh, there are 2 rows for that in table X. And so it matches X2 and X4, right? So what I will do now, I will take this row here and put it twice. So 3487464, and again 3487464 V02. So I will just have it twice with these 2 rows, which are here in this hash map, 2 and 4. And here we'll just copy row 2 and row 4. 2 and 4, which is Hutte and Burkhardt. And I think it's clear how this continues. And now I will not fill the table any longer, maybe just the next row. So the next row, now we are row 3. It's also V2040, and this is, it also matches. It's the same lookup again, X2, X4, and so on. And so here also, and so on, and so on, and so on. Any question about the hash join? Yes, please?
Also, you decide which table to use to do the hash map and which table to iterate over?
That's a very good question. So this is asymmetric. For one table I construct the hash map, and for the other I iterate over. Could have done it the other way around. It would have been correct. So that's something to understand, that it would be correct to do it the other way around. You would get the same result, maybe in a different order, but the order is not specified for correctness. So what would you choose? Think about it. Is this the best order, or would the other order have been better? What do you think? And what does it depend on? It's a very good question. Was this a good idea, or should we have done it the other way around? It's a very good question.
I think we
Yeah?
done it the other way around. We would have had 4 hash values
Yeah?
because there are 4 distinct
Yeah?
courses in table Y.
Yeah?
And we only had to iterate over 4 rows in.
Yeah, let me repeat that for everybody. So if we do it this way, we have 3 values, 3 keys in my hash map, and iterating over 6 things. The other way around, I would have 4 values in my hash map, iterating over 4 things. So with that knowledge, so is it better to iterate over more things with a smaller map, or the other way around?
The other way around.
The other way around. Okay. And actually, it fits nicely what's on the next slide, I think. Oh yeah, it says running time. So it's not an easy question to answer, but let's just see. Let's just write down what the running time is. It's a bit messy to write, but it's not really hard. So this is the running time, right? I'm iterating over so in this case, N1 is my X table, and I just constructed the hash map for that. And I have so many insertions, right? I create a hash map from this many values. So I have this constant Ni here. CL, I have this many lookups, yeah? So for one table, I insert into a hash map. For the other, I do lookups. So it's this times, so here's an asymmetry. I have this many inserts, this many lookups, and then I have this many, copying the result. So CC is also here. That's just copying that in there. So if I do it the other way around, then I have the CL here and the CI here. And a good answer to the question is that lookup is cheaper than insertion, typically for a hash map, which is why it's better to do the lookup for the larger table. But it's something to, maybe I could, let me just write it here. So I think in practice, CL smaller than CI, so N1 is good. Let me just write it like that, and please think about it and tell me if you agree. But and this H is not blue. Can you make a note and we correct it later? So, in the worst case, of course, the output could be the Cartesian product, and then we have gained nothing. But in this case, it was smaller. So that's one way of join, and that's the one you can implement by default, but maybe you also want to implement the merge join. So so join is really, every database engine will do joins all the time. It will not do Cartesian product unless it absolutely has to. So that's the hash join, here's the merge join. For the merge join, we need some sorting. For merging, we have seen merging in lecture 1, and we will now see it again. So this looks complicated, but it's really just the rows in sorted order. And then we can do merge. Merge requires sorted list, and that's the zipper algorithm from lecture 1. So we see a nice transfer here from the search engine stuff to the database stuff. It's actually very related on a deeper level. And this is, I will come back to this red thing, but let's first do it with an example and again. And I don't write the join operation, you know it by now, but let's just formally write what we have seen here. So what I need now is my 2 sequences, and let me just, did I give them a name here? No, join columns in, let me write a name. Let me just call this list 1 and list, maybe not list 1, but let me call it list X. And let's just write down these on the next slide. Okay, so what's my, just to make this perfectly clear, so my Lx is now, oh, let me also, so this is table X, this is table Y, this is the join column, and we are doing single column join, so we just have one, and this is the other join column here. That's clear. And now we want them in sorted order. So which of the, okay, let me also write that here. So examples will become faster and faster, but let's go slow, little bit slower in the beginning. These are my rows here. 4, Y5, Y6. And now I want, maybe it's not clear to you what I want, so I will just start. I want these sorted, and let's just sort them as strings. Which one is the smallest string here? From which row? What's the short? If I just, we want sorting on this. I mean, it has V here, so it's not a number, but we can still sort it by, what's the short, the lexicographically smallest string from these four? Which row? X1? Okay, lexicographically, I mean, if you compare them, I mean, that's the shortest string, but I mean, lexicographically, if like phone book sorting, which one is the smallest? Yeah?
X3?
Yeah, 3. Okay, so the order is, so let's just do it like, let me write it like this. So it's 4, 1304, and that's the notation from the previous slide is, let me just play around with the colors here a little bit so that it's super clear. That's 1. Yeah. And let's maybe first write, so which one is next? The next one is V2040, comma, and let me just leave and the next one I have it twice, comma, and the last one is V720, comma. And so, yeah, the order of the two does not matter. I have it twice, so let me just do it like this, and this should be, no, this is not 1, this should be 3, and the other one should be 1. Is this clear? So that's now the columns in sorted order, but I'm remembering from which row they came. That's the notation on the previous slide. Lexicographically smallest is V1304 from the third row, then come to 2040 from rows 2 and 4. Doesn't matter in which order I put them here, so I just resolve the tie by the row index, and last comes because 7 is large as this. And now you tell me how it looks like for Ly. And let's just do the courses first without the indices. Forget about the indices, just tell me the courses. Which one is lexicographically smallest? S, yeah, I agree. S is smaller than S03. And let's just, let me just put the row index here, but not for the others. I will put it in the end. So that's from row 6. Just have to, and you will see in a second why that is useful. Which one is next?
Y1.
Yeah, so V13, 04, comma, and I put the index. Which one is next? V2040, and I have to write it 4 times. So the repetitions are important here. So it's they are always important in databases. This is not Y, this is V. V2040, comma, comma, so I just write it V2040, comma, V2040, comma. Oh my. Yeah, I was, there's 2060. Who put that there? Oh my. Okay, 2060. Okay, now it's correct. Please, which number do I put here? 2? 1304, I put 2? 1? Which number do I put here? 2? Here? 3? 5? 4? Yes. Okay, that's it. So this is sorting. You're not only sorting, you're also saying from which row did it come from. So that's our input. That's what we have to do here. Let's go. And now we do zipper join. And zipper join, yeah, let me just write it. So now we do the zipper join. And I hope you remember it from the zipper merge, not zipper join. You could, yeah. No, zipper, how did we call it? Zipper merge. And maybe, so we have a result, and let me just write the result like this. And so how did this work? We have a, maybe let's take another color. I have a pointer here and a pointer here. And now I'm comparing these two. And I'm just doing the comparison on the strings. These are the values we are merging on. The rest is just a payload. So I'm comparing them, and I look which one is smaller of the two, the X or the Y thing. It's the Y thing, so I'm advancing in this list here. Now I have a match, and so now I output, I have a match here, so now I output the whole match, 1304, comma, and I just put the values from both column here, so that's 3 from the LX and 1 from here. And let me just write that here, so that's from X, from LX, and that's from LY. Okay, and let's do okay, and I can right away, let's maybe do that right away. So that's already my first result. So I claim that I have everything now to produce a result row, because it's just row 3 from table X and row 1 from table Y. So I will just do that. So let me just copy that. It's row 3, so it's my name, it's V1304, and it's row 1 from this table. So just imagine you are the program you are writing, 3, 4, 3, 6, and then because it's an equi-join, everything here should always have an equal column, sec 2 and 4. And now, so now we are here, there are no more 1304 values, so we can advance in both lists. And now, that's what was written on the bottom of the previous slide. Now I'm here, and now I'm at 2040, and there are matches again in both lists. And now I have to do something slightly different than in lecture 1, but it's also easy to implement. You just have to, now I have to do it. Now I have 2 values here and 3 values here. So I have to, so I have to take these into account, and these and these. So now I have to, if I have 2 matches of the same thing here and 3 here, now I have to do all combination. You have to do a little Cartesian product here. So inside your zipper join, when you have a match and there are K1 values here, K2 values here, you have to produce all K1 times K2 combinations. So there's no, the Cartesian product is always there, just on a smaller scale. And let's just do that here by just writing it. It should be there 6 times 2040. 2040, 2040, and 2 more times 2040. So that's what you're, okay, that's not easy. And now I have to write the, so that's now what you're, now I just write all the combinations here. So that's, I have 2 and 4 here, and I have 2, 3, and 5 here. So let me just do it like this, maybe. This is now up to the algorithm, how exactly it does it. 2, 4, 2, 4, 2, 4. And then maybe in this here I have 2, 3, and 5. And after that, let's just finish before we fill the table with one more row over there. So now I've processed this, and now I can advance to the last thing, which is V7202 here and V7260 here. There are no more matches. I'm beyond all lists, so this is the full result. And everything here, quite trivially, corresponds to a row over here. Let's just fill one more row. So this, actually I could draw an arrow here. So this one is now, I could just write this here, V20,040, and it's row 2 from the first table, which means it's Hutta, and it's 2 from here, so it's 3487464. Any questions about the merge join? So that's how it works. So it's a variant of the zipper join with the little addition that you have to do small Cartesian product if a value occurs multiple times in one or both of the lists. So you can implement either of them. Neither of them are too hard, but you have to get the details right, and then you have implemented a join operation. So let's look at the running time of this. This is a similar formula, and let's assume they are already sorted, so they are already given in that order, and that's actually an important question in practice. Maybe my tables are already in the right order, then the join is usually a good idea. If they are not, maybe you want to do the hash join. Yeah, so this, I'm not going into a lot of detail here because that's really from lecture 1. So I have the number of rows and the result row. So this is really CM. M stands for merge. It's just the cost for comparing or writing an element with zipper. Of course, you also have something for the, and this here is, it's the same as before. So what do we have here? We have CM. We have input plus output and a constant, and this is for producing the result. And let's quickly look at it again. You have to, oh my, now I've done something terrible. No, I don't think so. So this is n1, n2, n, and the result n times k. Let's quickly look at it for the hash join. Where was it? Here? Yeah. So it's also n1, n2, and something for the result. It's basically the same, except that I have different constants here. You have a constant for inserting something into a hash map, for looking something up into a hash map. That's the same. And here I have something for, the merge. The merge thing, that's quite simple what you're doing here, right? Imagine that you are doing this for very long lists with millions of things. This here is a very simple operation. You look at two values, compare them, write to the result. So this is cheaper than hash. Hash map lookup is a bit more expensive. So if the things are already sorted, that's what you want to do in practice. And that's what it says here. So asymptotically, they are the same if you disregard the constants, but typically this atomic thing which you do for one pair of rows is cheaper for the merge join, and so you would do that in practice if the things are already sorted. So for the exercise sheet, you need cost estimates, so let's just take those cost estimates. So you don't have the size of the input tables. They are again results of other operations. So you just take their estimates. N1 and N2 are now estimates. And let's just, we don't know how many of these rows match. Let's just assume that everything from the smaller table matches one row in the larger table. Completely arbitrary assumption, but some estimate is better than no estimate. And K is just the number of columns in the result. Look at this yourself when you implement it. This just all our cost estimates are very simplistic, but they are better than nothing. The whole reason for cost estimates is to differentiate between different query plans. And I conjecture that this is enough to say that this is better than the Cartesian product join. Your program should be able to figure it out. And we are completely ignoring these constants here. And just before the break, and there's question of the weeks also about this. So SQLite 3, what does it do? Hash join, merge join, Richard Hipp special join, Donald Knuth join. Don Knuth is the one who wrote these old algorithms textbooks from the 18th century or something like this. SQLite 3 does not have a hash join. And if you read it dubiously say an automatic index is about the same thing as a hash join. This is about the same thing. So you might want to read what the SQLite homepage has to say about that. Okay, so it does not have a hash join, so it surely has a merge join. It does not have a merge join either. Instead, what it does, it has to do a join. It does not compute Cartesian product. It has a join operation. It always iterates over one table and searches in the other. And then it constructs an index over one of the columns. And the hash map is kind of an index. Now you might wonder what's an index in this context. And this is lecture 6. So we have a new lecture which we didn't have 2 years ago, which is about indexing and more about SQLite special agent stuff. Yeah. So yeah, neither hash join nor merge join, which is quite special. And a typical, full-featured relational database system has both merge and hash join. And then it's part of the query planning to figure out, okay, in this situation, should I take the hash join or the merge join? And just to say that again, if you for some reason know that the tables are already sorted, you will always do a merge join. If you have to sort them first, you would rather do the hash join. Okay. And any questions? Otherwise, let's have a break now and continue after the break. Okay, break and fresh air. See you in 10 minutes. So, let's resume. Everybody here. Last row. Can you hear me in the last row? Great. So the second part, it's not particularly hard, but you have to pay attention. And as always, the most important part is to do the exercise sheet. Let me briefly talk about the exercise sheet. So it's implementing the join. Do a hash join, it's simpler, but maybe you also want to do a merge join. Maybe you're feeling lucky and you want to do both the hash join and the merge join. It's certainly worth it. And you should, so far you had these crazy Cartesian joins, which took forever. And you should actually be able to be faster than SQLite if you do it properly. So that's a challenge. Try to use it as motivation to do the sheet. And then there are more operations which I will explain now, which are actually simpler. So once you have done the join, so the first part of the exercise sheet, the rest is much simpler. So you do a join, you do group by, order by, limit and offset, and then you run your own engine on this nice query, which is like the top 20 actors in popular movies. Yeah. So actors who have been in a lot of popular movies, and then their average score, which is quite an interesting query, and you will execute it with your own engine. So with all these operations, you can actually compute pretty interesting queries. And I will come back to exercise 3 on the in half an hour or so. And here's the the question of the week. What does it say about humanity that the most used database engine in the world has neither a hash join nor a merge join? It's a very interesting question. Not only what does it say about SQLite, what does it say about humanity? Research a little bit, think about it. I think it's an interesting philosophical and technical question. Okay, and please do the exercise sheet. Listening is fine, but really the sheet brings it home and anchors it. Otherwise you have to do it when you prepare for the exam, because exam questions are just what you do for the exercise sheet. Please do the exercise sheets. So more join operations. We have seen the single column equi-join, which is no doubt the most important join, but there are others. And also it was specific in one more way, which I will now explain. Let's just go to the example again. Everything else will be simpler now and less tedious. Where did we have our, So here, we had these matching rows here. The green one gave one result, in the result table. This orange one, we had a little Cartesian product here. And the other ones, they were just dropped, right? The join is smaller than the Cartesian product. This one was dropped because it doesn't match anything here. This one was dropped because it doesn't match anything here. Now there is a way to specify if this doesn't match anything here, please still include it in the result, and the other way around. And that's what we will talk about now. It's easy to understand if you understood everything so far. So what we had now is inner join, only include results if they match. And there's left outer join, depending on what I just said. If something here which doesn't match here included, that's called left outer join. Right outer join, if something matches here but not here, included, or both ways outer join. I don't give the definitions here. You can implement them, you don't have to implement them. Actually, if you implement a join, it's not hard to also implement left outer, right outer, and outer. And these four combinations, they are really, really frequent in practice. Sometimes you need all of them from time to time. Let's just look at an example. And that's one way to write it. So you have the same tables we have been using all along, profs and studis. And we just write left join on. So that's a little new notation here. I will talk about this more in a few slides. Instead of writing profs, comma, studis, just the two tables, which is always, if you have a condition, an implicit join, you can write in SQL the join keyword specifically. So this table, left join on this table with this equality, and this should be the exact same tables, and now this is the result. And let's just spend a little time to clarify it, but maybe you get it just by looking at the table. Let me even use the same colors as before. I think we had this one here, this matched, right? We had 2 here, and we had, was it 4 or 3 here? I think 3. This one here, and this one here. I think I've added one more row to my table, but doesn't matter. And then we had the other one, this one was green, I think. This matched, so those were matched by the inner join, and they also match in an outer join. The outer join is a superset of the inner join, and let's just find this here. This is here, this corresponds to this. And I won't do it for the other table, I will just do it now. And here we have this big 6, little Cartesian product thing, 2 times 6 here. And now it's a left outer join, so everything in the left table, that's why it's called left. And let's do it with this wonderful color here. This doesn't match anything in the other table, but we still include it in the result. And you see how it's done? I mean, in the obvious way, it doesn't match anything. How often do we include it? Once, exactly once. And we can't put anything here because it doesn't match anything in the other table. So we just put null values there. And let me just, So this is my table X, this is my table Y. This here corresponds to X. This corresponds to Y. And I think if you see it by an example like this, you have understood left outer join. That's left, or left join. You don't write the outer. I think you can even write the outer. In SQL you have many ways to write the same thing. I think this pretty much defines left join. Any questions about it? Now let's also see a right join, and I will not do it in the same level of detail. That's now the right join, and maybe let's just, now where's the row in the, let me not just do all the colors again, so that's X, that's Y, that's X, and that's Y. So let's find the values in the right table which don't occur in the left table, and this one does not occur. In the left table, 240 occurs, something is wrong here. No, it's not. Something is, no, it's fine. It's this one, right? The others all occur in the, does not match in X. And we have these two here, I hope, yes. Any questions about the right join? Just the same way, the other way around. And I don't have an example for the full outer join. For the full outer join, you just do both. So you would have that table where you have both that row, where it doesn't only matches, it's there on the left, but matches nothing on the right. And you would have this row, it's there on the right, matches nothing on the left. So if you have outer join, it would have one row more here. Any questions about outer join? Yes, please.
For the complete outer join,
Mm-hmm.
the difference between it and the Cartesian product is in terms of computation, both would again be the same, since it's more of a union if you are including both the tables.
So the question is how you compute it, whether you have to do the Cartesian product?
Its computation is similar to the Cartesian product, because in that you are including all possible combinations, and in outer join again you are including everything.
So it's a good question, and would be also an interesting exam question. So is this, if you have outer join, the result becomes bigger because now you have everything from both tables. Does it have the same size now as the Cartesian product, or smaller? What do you think? Yeah?
It's smaller since you don't include all combinations.
Yeah, you don't have all combinations, right? Actually, you see it. Let's go back to this one. There you see it more clearly. I have more results, but I don't have this multiplied with the size of this table, right? In the Cartesian product, I would have this thing 1, 2, 3, 4, 5, 6, 7 times. So that's why it's smaller. And actually, the most that can get added is 4 from here and 7 from here, so linear. And actually, it's worthwhile going back to our merge join algorithm. I think, and that's what I just said, if you want to implement it, just imagine, go back to this merge join, and now you want left outer, right outer, or full outer. It's not hard, right? You are here, 1304. It doesn't match anything here, so you just progress. It doesn't match anything here for the inner join, we just skipped it. Now we can just say it doesn't match anything, let me copy it once. It would not be hard to do, right? At this point here, just copy it once. This one also copy it once if it's a right outer join or a full outer join. You would just add at most a linear number of rows to the table complexity would be essentially the same. Yes?
But wouldn't it be the same as the Cartesian product if we only had one course?
Oh yeah. If we only had one course, no. The Cartesian product is always the product in time.
But then for the outer join, wouldn't it be the same as the Cartesian product?
If you say if we only have one course, what do you say? If everything is distinct here, or what's exactly your condition? Or what are you asking? So if it's 4 here and 6 here, then no matter what's in these fields, it's always 24 in the Cartesian product. The Cartesian product does not care about the values. Maybe think about it. If you have a different question about it, just ask it again. So this is cheaper. And another interesting question, maybe let's not explore it now, but think about it. Also an interesting exam question. Mental note. All these, yeah. Maybe it motivates you, but it's actually interesting. If you want to do an outer join, left outer or right outer, can you also do it with this algorithm? So when this is asymmetry, right? For the merge join, I think it's pretty clear that it's easy to do left outer, right outer, both outer. If you have this one, is it also easy to do it? Think about it. We don't have to do it now, but it's so that's outer join, and let's natural join. What's a natural? Now organic, biological, organic join, natural join. A natural join is just an equijoin, and it's actually, we have been doing natural joins all along. You just didn't know it, because here, this column where we join is called course, and here it's also called course. And that's actually, you have that pretty often if you have a good table design, which of course is in one. You will not have, they will be called by weird names probably, and it's one reason for the... So you see it here, it's table blah dot course equals table blah dot course. Yeah? So it's the same variable names in both columns. And that's actually, in a good design, not so infrequent. And then you can just, so this here, we have it again. No need, there was no need to jump back, but now we have it here again. And then you can just say natural join. So all of these three are equivalent. Let's look at it again. That's how we have been writing it in the last lecture, in lecture 3 and lecture 4 actually. 2 tables, cross product, and then aware. You can also write it like this table join this table on, and then you write just what you would write for the where. Or, because it's the same column name here, let me just emphasize this. So this is because this here is equal. It's course for both. You can just say Profs natural join Studis. And it would also work if they have more than one column in common. No question?
My question was,
Oh, yeah. So if there are 3 columns with the same name, it would do a multi-column join. Yes, I hope so, but I would expect it. But yeah, I don't see that a lot written. So the question is, what do you use in practice? As I've said before, SQL has many ways to do the same thing. That's a more philosophical question. Is that a good thing or a bad thing? Some also programming languages, some say it's good that you have 500 things to do the same thing. Others say it's bad, there should be exactly one thing, and in a good way, yeah. I think Perl, the scripting language, is famous for there being 500 ways to do the same thing, and 500 equally weird things to do something. There's more than one way to do it, was, I think, the mantra. So I think the second is the most modern formulation. The first one is like the traditional one. That's how I would write it. The third one, I don't see that a lot in practice. non-equijoin, you don't have to write equality constraint. Then, of course, you can't have these implementations. So our hash join and merge join strongly relied on this being equality. Otherwise, it wouldn't work. And here's just one example. Let's say we have bus stops and restaurants, and they have points on a map. And now I want all restaurants near bus stop, and let's say within 500 meters. And this is, yeah, here you see that the Cartesian product kind of makes more sense. It's actually how you might want to compute it. Let me take all combinations of a bus stop and a restaurant, and let me check if they are within 500 meters of each other. And if yes, output the result. This is called a spatial join. And actually you can do sophisticated stuff, and we actually do research on this, quite a big topic in our group. How can you do pre-processing such that you don't have to compute the Cartesian product here either, but do it efficiently. And SQLite also has something, and it's called spatial light, which so that you can do these things a little more efficiently. So, some other stuff that's now simpler, so let's go through it more quickly. Grouping. Here's the grouping. Let me just go through here's the definition of grouping. That looks scary, right? Let me just, so this is we will see an example. You will see that it's actually super easy. It's just hard to formalize. You don't have to understand this now, but while I'm writing something here, you might want to try to understand it. But it's not so important. The example is, so actually P of x it's the power set. No, not power set of x, which is the set of all subsets. Power set of x, which is the set of all multi-subsets. We have multi-sets, so it's all multi-subsets. But that's just notation. I don't go into any details here. It's just for your reference. And also to understand, let me maybe quickly go to the code template. Because we have, where is it? In operations.py, right, Robin? Operations.py. The code template for group by. Yeah. And I think, where do we, let's come, this, what we are seeing here is actually strongly related to the signature of this. And let's first go to the example and then back to this. This is a good example where understanding the interface is harder than actually implementing it. Once you are, and that's often the case in programming, which is why these exercises are extremely important. So let's just look. This is actually much easier to understand than the previous two slides. So we have a table with movies, and just the title of the movie, the year, and the score. So we keep it super simple here. And now, as you can see, there are several movies here from 2022, 2 from 2021, and 1 from 2023. And what do we want from each year? Not the movie, but the highest score from each year. Yeah, and that's the result. I think that's simple enough, right? So from 2022, let's just look at it. Let's just do it for, why not do it for all of them? From 2023, we just have 1. And so what the group by does, so it's grouping by year, so we just have 1 from 2023. It's grouping them all together. Here it's just 1. And then, so this is the group for 2023. I have exactly 1 row for each group. And that's the maximum score. There's just 1. It's 8.5. Let's also do it for these 3. They don't have to be consecutive. They just happen to be consecutive here. That's 2022. That's here. They also don't have to be in order in the result. And let's do 20. Yeah, what's a nice color? Purple. Any question about this group by example? I think that's simple enough, right? So we have these three, and you just say, what do you write in this column? That's an aggregation. I take all the scores from this group, which have the same year, 867877. The largest one is 86. Now let's take some time to explain the operation, which I defined on the previous slide. I will not go into it. And then quickly to the exercise sheet for those of you who want to do it, which hopefully will be all of you. So you say the operation takes one table. It's one table which you group. So you put everything here in group and output one line per group. You say on which column do you group, which can be a single column, can also be multiple columns. So here I just have year, and I will have one row in the result for each distinct value here. So in this case, 3. And now I have to say if I include other columns, so I'm grouping by year, and I want to include score, then I have to say, okay, for one group I have multiple of them, how do I aggregate them? Yeah? I have to say what I group, that is this argument, can be one or more columns. And for the columns which I don't group, I have to say not group by, how do I aggregate them? So column 3, I compute the maximum. Could also be average here, or sum, or just count. And also note, I don't have to include every column. Title, I just ignore. Yeah? I could also do concatenate, like concatenate them all together with commas as a separator. And that's exactly what you see here. So the columns is just the columns by which I group. In my example, that's just one, but it could be multiple. And the aggregations is just for a selection of the other columns, an aggregation function. So it's, if you understand it, it's actually simple. And what's an aggregation function? An aggregation function takes a list of values, which for example is these 3 scores, and produces one other value. And this is, let me just say that again, that's why, yeah, if you understood it, it's actually not hard, but if you see this for the first time, you say, oh wow, this is super complicated. It's actually not complicated, it's just translating what is pretty obvious to code. And this is super general. With this you can do any state of the standard group by. Any subset of the columns, aggregation, whatever, any aggregation function, no need to commit to a particular one. And here the code template just has all kinds of asserts. If you group by, you have to have some, one constraint. You're grouping by year, you are aggregating the score, these have to be different columns, right? This 3 here must not be in this set. You can't group by and aggregate the same thing. So all the columns here must be disjoint from all the columns here. But columns can be left out. There's having. Why do you need having? Becomes clear by another example. I will skip the previous slide. So this is now, it's just a group by with an additional thing. And let's just, you can read the slide while I write some stuff here, maybe in wonderful orange. So what's the maximum for, let's just do 20, for 2021 we have, it's the maximum is, no, I don't like orange. I will do it in blue. And while you read this, think about why do we need something specific for having? And I will ask you in 1 minute why we need having and why can't we do it with the stuff we already have. When you introduce new keywords or functions, you have to ask yourself, why do you need them? So for 2021, we have the maximum is 8.0. me just write them. Question is, why do we need a new keyword for having? Max is 8.0 for 2022. The max is 8.6. Yeah, it's just 2023. The max is 8.5. And so for each of them we have to check this condition. It's greater than 8.0, so we should have here the greater than 8.0, greater than 8.0. 8.0 is not greater than 8.0, so we don't include it. Yeah, it's one less than on the previous slide. And now my question, why do we need that? Why couldn't we have done it with regular constraints, which we already have? Why do we need having here a new keyword for this kind of functionality? We already had where, whatever property, right? Why can't we do it with where? With the typical select from where, and then in where we write score. Yes?
Because the max score is not a column of the original table?
Yeah, that's a very good answer. The max score is not, this is a property on something that's not in the original table, right? It's a property on max score. Max score is not in this table. In the where clause, I can only write conditions on things from the table. Max score is actually the result of an aggregation, which is something the group by computes. And sometimes, and this is an example, you want a property on something which is a result of the group by. And that's why this is the having. Having is post-filtering after the grouping on stuff the group by computed. If it's not clear right now, think about it. That's why you have having. That's not only why you have it, but why you need it. You couldn't simulate it, or at least not easily, maybe with some monster query. Okay, that's group by with having. And it's actually simple enough to incorporate into the operation. I don't think it's in the, is it in the code template? It's not, right? No, we don't have having here. It's already complicated enough as it is. Yeah, cost estimates, so implementation is part of the exercise sheet. Again, if you understood the interface, it's 3 lines of code. So writing your database engine, the simple one, which is really nice exercise, I highly recommend it. If you understood the code structure, writing the individual code pieces is actually very easy, and you end up with something that's faster than SQLite. I think that should be very motivating to try this. So for the group by, just take this cost estimate. So you have to go over the whole table to group things. So that's why the cost is n times k. How large is the result? Arbitrary, let's just say groups have size 2 on average, and that's the number of columns. If this is the output table. Actually, yeah. Think about it, it's just, as usual, our estimates are super simplistic, but better than nothing. Let me just say that again. The estimates don't even have to be precise, they just have to be good enough to tell a really bad way of doing things from a better way, especially not do Cartesian products. Yeah, here's what yeah, and the aggregation function can be something crazy. I don't consider it here in the size estimate. That's the last exercise, and please do it because it actually has been. It's a typical exam question. I mean, it's true, it's an exam question. And maybe it's not clear to you from just seeing this, that this cannot be done so easily with what we have seen so far. For each year, I want the movie with the highest score and the corresponding title. And let's just go to without the having to this one. And please think about it so what have I done here? For each year, the highest score. And now I want 8.5, I wanted to say Oppenheimer here. And for the 8.0, I wanted to say Dune. And for 8.6, I wanted to say Kashmir Files. How do I do this? Yes?
So I would go for select year, max score as max score, and also title. Your movies group by year, having score, like having the table name dot score equals max score.
Oh, you wanted to do it as a having?
Maybe if it's possible.
Oh, that's a clever idea. Does it work? So you want select year. I don't think it works because you have the title, you have to include it as an aggregate here, right?
Okay, so I can't just use it in select.
No, that's the problem. But it's a very good idea to use the having. But I think it doesn't, that's exactly the, and let me just, it's a very good idea, but let me say that again. If I want to include title in this select, I have to aggregate it. So I have, and how do I aggregate it? And what I want to say is, pick this title where score was the max score. I mean, I just can't say this. The aggregation just says I could pick the one with the most characters or so string length, the one which is lexicographically smallest or largest, but I can't, I have to specify a function which picks one from these three. But actually what I want is, I want the one where the score is the highest. So I want to pick one relative to some other aggregation. And this is just not possible with normal group by. But you have to do it anyway, and that's exercise 3, and I will give you one hint now, or in a second. And it's actually a really, really frequent query, and you have to know how to do this. So, this is what I just said. This gives you the highest score. How do we get the corresponding movie? Having was a very good idea, but I don't think it works. Only allows per column aggregation. If it's not clear from what I just explained, think about it. It's important to understand before you have the solution also why isn't it so simple. And a few more slides and then you will see a hint at the reply. But let me just go to the exercise sheet and show you. So it's, here you have a similar query. So for each, again, IMDb, we just want the best movie from each year, which is a very nice query. From each year, what was the top movie? Not all years since humanity, maybe starting from 2010, so that the result is not so big, 15 or 16 rows, and we only want movies with 500,000 votes. Because there are movies with 3 votes, so just 3 people watched them, but everybody gave them a 10, and then the rating is maybe not. So the IMDb scores only says something if you have a lot of votes. So that's, the result is actually interesting. You get the best movie from each year. You can also use it, best movie from the decade. And that's exactly of that kind. It's easy to get the best score. How do you get the movie with that score? We'll come back to this in a few minutes. We are almost done. So the last slides are just a little more SQL. SQL is a monster. I already said that. This, as Robin pointed out, is just part 1 of the standard. There are how many parts? 6 parts, and each of them costs hundreds, or even the sum is, if you aggregate, the sum is 1,000 euro at least, or Swiss franc, or whatever. And if we click on it, oh, now it works. We had the same Cloudflare issue. So this one also works again? Yes. Stuttgart works again. So the Cloudflare issues have been resolved. So here you can buy the standard if you have problems sleeping at night. I think that's a very nice way to just start reading so it's expensive, but absolutely worth it and more healthy than sleeping pills. So, and in this course, we will just give you a few more basic ones. But the basic ones are enough for a lot of things. And actually, as I said, each engine has its own dialect, and here you can see what exactly SQLite supports, but everything we explain here is of course supported by all engine, because it's really the core. We will now see order by, limit and offset, and subqueries. Subqueries is what you need for what I just said, for this movie thing. And they are super frequent. Basically every query, which is a little more complex, needs them. Order by, and they are easy to explain, so just bear with me for 5 more minutes. So far, order, there's no order. There's no order in the input tables. Of course, you always write them in some order, but the engine can permute them or whatever. It's not in the definition that something should have a particular order. Same for the result of operations. But sometimes you want an order, which is why in the end you can always say, okay, order this. And that's why you have order by. And order by is just take my table and order it in a certain way. And here's a simple example. So I have my movies, and there's a scores column. Order it by score, descending, which means highest score first. And you can have complex functions here, you can have multiple things. So if the score is the same, use the year as a tiebreaker, like the most frequent year first, and so on. I think it's pretty obvious what the semantics is. And of course, if you have a group by, the order by has to come afterwards. Let's just see it in our example here. Yeah. So if this is my result, and now I want to order by max score, the order by should come after the group by. So it's always first group by, then order by, and then these two would be swapped. That's order by. Here's an example. Select year, max score from movies, group by year, order by year, ascending. So here it's actually, I can order by the group, also by the aggregation. If I've ordered the table, now I have a table with 1 million columns. I want some kind of pagination. I just want the first 100 rows, the second 100 rows. Yeah, this is also pretty obvious. So here I have the top 10 movies by score, highest score first. Maybe then I want movies 10 to 20. Then I do offset, start from 10 and the next, and so on. Yeah, so this is now starting from the 10th, the next 5. Limit, offset. It's very easy. So you do group by if you have a group by, then you order by if you care about the order, and then you can say just this part, please. And this is the most frequent. Just give me the first so and so many. Offset if you really want to do pagination, page 1, page 2 of the result. So that's what I just said. And now subqueries, last thing to pay attention to, and this is what you need for exercise 3. So this needs a little more attention, and I think you will probably not fully understand it right now. You need to look at it afterwards and do it yourself with an example. First, understand every operation we have seen so far, and all operations, they take tables as input, do something with them, and produce another table. And this table is input to another operation, and so on. In the end, you also get a table. Everything is tables in databases. Now, a select query, like the whole thing, also has a table as a result. So, what you can do is, you can write a whole select and then continue with that. So here you have a SQL query, so I have a select on the outside, but as part of my query, here join, and the argument after a join usually comes another table, and usually so far we wrote here one of our input tables, but instead now I have a computed table, which is computed by a whole other select query. And I hope you agree with me that at first glance it's not easy to say what this computes, right? Now if you start nesting things, it already becomes a little more complicated. Select title from movies. Let's take maybe half a minute. Do we have a different idea what this computes if you look at it? What does this compute? it's only one more slide, so let's take a minute to. It's not easy, but possible to figure this out. Who wants to answer? Yeah? Okay, the suggestion is movie title where the director won an award. That's a good suggestion. How did you come up with this? You first looked at the subquery. That's a very good idea. What does it compute?
It just gives me a list of persons who win an award. Only one line, only one row per person. So if a person won multiple awards, it doesn't matter because we use the listing keyword. And this subquery results a table which is then called awardees. And then we select the titles from the movies and join it with the directors table and check if a movie ID matches the director movie ID. So if the current movie is actually directed by our director, which is the join, and then we check if the director is actually the holder of the award.
It's a perfect explanation, and let me just repeat the essence of it for everybody. So that's exactly right. The approach is, if you want to understand such a query, it contains subqueries, understand the subquery first, right? And because this subquery, it could have been an input query. And what's the subquery doing? You can actually, this one you can read almost like a sentence. It's for each person and distinct, so you have each person one. Doesn't have to be a director, an award. And actually, it's not true. It's not the award, right? It's only the person. So it's a table with one column. Is that correct? And it contains each person that had won an award, and which award? Academy Award. Any one of them, Oscar. So this table is just a table with one column, and each entry is one person, and they have won an Oscar. For anything, doesn't have to be a director. And this could have been one of our input tables, but it's not, but it's something we can compute. And this as even gives it a name. Could have been in the input, it's not. And now if you just remove this whole thing and just put this table, awardees here, and then the rest of the query is not so hard to understand. Then it's just, directors who are in this table. And you absolutely, if you weren't that fast now, that's totally normal and fine. Try to understand it at home. So that's what I just said. This gives us a table. So just do as if you would have had these tables, movies, directors, and awardees. And this table was actually computed. It wasn't there. And then this whole query is just this: select title from movies, natural join directors, natural join awardees, and this is much easier to understand. It's basically when you have complex expressions, you start from the inside and then you just move outside. It's not really hard, it's just frightening at first. If you see this, it's frightening, you have to simplify it. And I don't want to spoil it for the exercise sheet, but you absolutely have to do this. As I said, typical exam question. For this kind of query, you also need a subquery-like thing. And you have to do this once to understand how to do it. So this, when you want group by, and you do not only want the highest score, but also the movie with that score, you can solve it with subqueries. And that's it. So that's the exercise sheet, that's the exercises, and we are, despite starting late, on time. Do you have any questions right now? Okay, please do the exercise sheet and see you next week. Bye-bye.